take about 30 minutes for me too. Order 1, July 17th. Alright, I'm going to do it early today because tomorrow I have to wake up early. Which is quite bonkers. Haven't waken up early for a very long time. Alright, what do we have? Oh, why is this happening every single day? Is it me? Or is it LeetCode? Doesn't make any sense. Okay, let me see if I refresh this. Does it take a long time? I think it's not me. I think it's them. For whatever reason, it just gets slow. Alright, number of good leaf nodes pairs. You're given a root of a binary tree and an integer distance. A pair of two different leaf nodes of a binary tree is said to be good if the length of the shortest path between them is less than or equal to distance. Return the number of good leaf node pairs in the tree. Okay, so basically we want to find all the pairs of leaf nodes, not any nodes, it's just leaf nodes. So all the pair of leaf nodes whose distance is shorter, less than or equal to the distance. Okay, the first one is here. The leaf nodes of this is 3 and 4. And the length of the shortest path between them is 3. 1, 2, 3. So the answer is 1 pair. So basically what we need to find is the leaf and the shortest distance, shortest path between the leaves. Okay, so how do you compute the shortest distance between the leaves? Well, you are going to have a bunch of leaves, right? And yeah, that's not going to work. So this is 3. So basically we have 4, 5, 4, 6, 4, 7, 5, 6, 5, 7, and a 6, 7, right? And then 4, 5 is good because 2. 4, 6 is no good because anything, yeah, you go onto the other tree is no good. 6, 7 is good. 5, 7 is 4. So that's also not good. Interesting. Okay. So we will know the distance from the root to every node. Or we can say when we go to, since it's a binary tree, so the shortest distance is very simple to calculate. All we need to know is the lowest common ancestor of the two nodes. So are you saying we're going to do lowest common ancestor for every single pair? That seems to be excessive. That seems to be excessive. Very excessive. I kind of don't want to go there. Because we can just write, give me two leaf nodes, tell me where is the lowest ancestor. And then what? From the lowest ancestor, I need to know the distance from there to the leaf. But I do not know, right? I do not know. So I need to create a data structure so that I know. So once I grab, how about this? At each root, I will recognize all its, I'm just thinking out loud, right? So at 1, we know its leaf is 4, 5, 6, 7. I know its distance is 2, 2, 2, and 2. Therefore, if I need a pair of leaves within this group, they will all have to go through 1. And then the distance will be 4. 4, right? So now 2, we have 4 and 5, which is 1 and 1. 3, we have 6 and 7, which is 1 and 1, right? And because of this, we go through them, and the thing is, and I also know, what is the number of nodes? 2 to the 10th. What? The number of nodes in the tree is in a range of 2 to the 10th. What in the world? Are you kidding me? Are you kidding me? 2 to the 10th. 2 to the 10th. I can't even go through everyone. Yeah, I can't even go through. Like, how do I even do BFS or DFS in this? And I absolutely need it. I mean, we have to, like, there's no other way. But even if we do it, if they get 2 to the 10th, Jesus. 2 to the 10th, how much is 2 to the 10th? Oh, wait, hold on. I thought it's 10 digits. That's not 10 digits, right? Dude, what the hell? 2 to the 10th is not. It's 1002. Oh my god, you are so dumb. Okay, my bad. I blanked out right there. I thought it's 10 to the 10th. Okay, 2 to the 10th is fine. Totally fine. Okay, so we're gonna BFS this, and for each one we're gonna get this. Okay. Oh, that is nasty. That is nasty because the values are not unique. That's fine. The value is not unique. The value is not unique. Yeah, I feel like we have to, oh my god, I have to write that, right? Lowest common ancestor, we have to do that. So we need to know the distance, right? We need to know the distance so we can find its lowest common ancestor. But I'm not using binary lifting to do this. I will use the other method, right? I'll use the other method. I kind of forget how that method works, so I'm going to think about that again. And we're just going to collect, we go to the root, go to the leaf, we collect. So we have, leaves, right? We're going to just have the whole thing, everybody in the leaf. And then for everyone, we're just going to check with everyone. Everyone we check with, so it'll be O(n) squared there, but it's fine, okay? Because in total, at most is 1,000 nodes, right? So we do that, and each pair we use the method to find its lowest common ancestor. So next question is the lowest common ancestor. What is the distance from there towards our node? That is something I do not know. Okay, that is something I do not know. Now there is a question which I wonder. So in Java, right, can I have use an object as key? Is that possible? I mean, technically, it will be translated if it be translated into, you need to implement hash code and equals on key. Checks for instance equality. Wait, does that mean we can? That's fine, but that's fine by me. And expect them to be equal. So they are not equal, right? That's exactly what I want. Okay, I don't want them to be equal. I want them to be different. Hey, look at this implementation. At override. I think I've seen this before in someone's code when she's trying to write a unit test. All right? Okay, so this is exactly what I want. I do not. So if I have a node which has a value of 4, and I have another node which has a value of 4, I want them to be different. I do not want them to be the same. So this is exactly what I want. Okay. Therefore, we are going to go through one DFS. So we'll pick up everything, right? So it's gonna be, oh, holy crap! This is gonna be interesting. It's gonna be a hash map, right, with each root or subroot node, and they will have another hash map which contains all of their children, right? So for whatever it is, I have a left child, a right child, so I get all the kids here and all the kids here, and I'll combine them into a new one where their length, the distance will add 1. So now I have this, I have this, I have these two ready. Then
You scheduled a new townhouse?
No, I did not, because I gave a time, but I'm waiting for them to respond. And that expensive one is saying if Thursday's working.
Did you say Saturday or Sunday?
I did, but he said, I'm doing showings to grow. And wait, what? And I was wondering if this Thursday worked for you to view the available townhouse. I'm gonna say no. The earliest we can do is
We can only use
Saturday. Yeah, unfortunately.
For Friday? Friday at 6 p.m.
The earliest we can do is, we can do Friday. Calendar, let me see. Friday we can do at 6, yes. The earliest we can do is Friday 19th at 6 p.m. And then we can do Saturday is 104. Actually, I cannot do 4 anymore because I got it scheduled. We can do Sunday.
That's fine. Do it after LeetCode.
Oh, I can also do. 2 p.m. or 5 p.m. Actually, we shouldn't say 2 p.m. We're gonna do a lot of driving, unfortunately. Alright, let's go back to what we're doing. Then we are going to write. Okay, how do you do the lowest common ancestor in a binary tree? So if I remember correctly, we're gonna go left and right. We check if the left one is the target. Right, we check if the left one is the target. We check if the right one. How to compare two objects the same. All right, compare two objects the same. Equal sign compares two references identical or not. Compare two objects. Objects are equal when they have the same state. Objects are identical when they share the class identity. Compare two Java objects.
What about this? This plastic for my leucine.
Yeah, I think that's fine. I think we There's only so much we can do. And I think the best we can do is do not microwave plastic.
But there ain't point that our food comes in plastic.
What's the point of life, right? Yeah. Now I think we do the most we can, and then what I think, at least for me, is do not microwave plastic. Do not microwave anything in plastic. Yes, because these are two different classes, which means the equal sign will work for me. Okay, I think it will work for me. Okay, so if you are a ancestor of both, right, then you will be so your left, your right, or yourself, all the three will contain all of them, all the two children. And the first one that does it is it the first one that does it? It's not necessarily the first one that does it, right? No, it is the first one that does it. Because we go from the top, right, and we don't do it, we go left and right first, right? So it's post order. We'll go left and right first. So whoever get it, then we just return. True, right? We return. Yeah, we'll return. Otherwise, we return null. No, that's not what we return. What we return is does it exist, right? Does it exist on the left? Does it exist on the right? And if myself, right? Myself exists as count 1, and then we go left, and then we'll return a number, how many exists. We return go right, we return a number, how many exists. Yes. And if the count is larger or equal to 2, that means we have it. And we shall check also that if it has been then we just return -1, or we return a minus big value, right? We just return big minus value. Really? Is that the one? Okay, I need to refresh the memory on this one. What is the solution for this? The good solution for this? Yes. Found left, found right. Found self. Larger equal to 2. Self dot rest. Otherwise, return this or this or this or this. So that is the problem. I always was wondering about this part. If later I find something, isn't that gonna right? Because you OR them, so you only return 1. Found left, found right. Oh, this is smart. Because if you're a common ancestor, then you will have found right, found left, but you're only returning 1. So any of your ancestors will only have 1. Holy crap, this is smart. And this is what? This is because you have to traverse the entire thing. This is ON, right? This one takes ON because you're going through the whole thing to find it, which means if you have ON times Q, this is ON, right? This method is ON. I didn't say if it's ON or not. Yes, it is ON, right? It is ON. Okay, so take ON to do this. So take ON to find, and then we'll have n squared pairs. Dude, it's gonna be ON tripled. Really? It's gonna be ON tripled. I feel like they gotta be something better. They gotta be something better than this. No. I don't want it that way. I think I want this the other way. We have each leaf. Okay, so we have each leaf. We have the path. Okay, so 2 and 1. 5 is 2 and 1. 6 is 3 and 1. And 7 is 3 and 1. Alright. And then for each pair, so this pair, there is a common ancestor, so it is 1, right? It's 1. And common ancestor. No, we need to go from right to left, right? Go from right to left to find the first one that does not match. No. The way we do it, it's not gonna be like this. It's gonna be the parents goes first, right? Parents goes first. So 1, 3, 1, 3. So if with these two, we should go okay this, and then we find the remaining. So in this way, it is going to be ON squared. Okay, because we don't know. It's what's the last row? Well, we need to do ON to get this one, right? And then the last row, I think, is so this is like 1, 2, 4. It's double, right? It's double. So this is on total is 2 to the 3 minus 1. 1, 2, 3, 4, 5, 6. Yeah, 2 to the 3 minus 1. And the last one will be 2 to the second. Okay, 2 to the second. So whatever it is, it's going to be n divided by 2. Okay, so it's still ON squared. ON squared to get through all of them. And then we're going to go to, this is basically the height. And the height is in the log n. So ON squared log n. I think that is the solution. ON squared log n. Okay. I'm not going to use the other method. It's going to be this one. It's different. All right, let's do this. So first things first, we need a private void DFS tree node. That's not what we want. And every time we do that, it will delete the entire thing. I do not like that. Void DFS tree. Like if I do this, I have just a tree node. Yeah, sometimes you just need to ignore it. And we can go delete that. Right, it's fine. We don't need those things. Okay, so we need to do that, and we probably need another one, which is called map tree node. I'm not even sure it's possible. Tree node and an array list of tree node. Holy crap. Paths. Leaf path. hash map. Okay, okie dokie. So what we're gonna do is we have a tree node and we need a path. Right, and list tree node path. So of course we add ourselves first. So if node is equal to null, we'll return, okay? And then we'll say path.add node. And then we say if node.left is equal to null, and node.right is equal to null. So this is a leaf. So when we find a leaf, we need to say this dot leaf paths dot put node and path dot. Do I have a copy? How do I copy? Or maybe I can just do new array list of paths. Probably this is a copy, right? So if it's a leaf, we do that. Else, if it's not a leaf, then dfs node.left, dfs node.right. Okay. All right. So we will do this, and this is not right. And don't forget path.remove, path.size -1. Okay. All right. So that's that, and we will just do dfs root new array list. Okay. So now we have the leaf path, and then we also have the leaves because they're stored in leaf path. We can say list of tree node leaves equal to new array list this dot leaf paths dot key set. Okay, and then we can say for int I 0 I smaller than leaves dot size I plus plus, and for int j is I plus 1, j smaller than leaves dot size j plus plus, right? So we have both. Now what? Now we have ij, so we need to pull them out, find their so we have a k, right? For int k equal to 0, that's actually not true. K equal to 0 while k is smaller than this dot leaf paths dot get, holy crap, dot get leaves dot get I dot size, and k is smaller than this dot leaf paths dot get leaves dot get j dot size. Okay, so we have these two. So while this and holy crap and what, and the two are the same, right? And okay, I need to redo something. This is not working. We say list of tree node p1 path 1 equal to this dot leaf paths dot get leaves dot get I. Okay, list tree node actually we did this again, 43 p2 path 2 this dot leaf path dot get leaves dot get j. Okay, And then let's delete everything. K smaller than p1 dot length, not length. P1 K smaller than p1 dot size, and K smaller than p2 dot size, and p1 dot get K is equal to p2 dot get K. If that, then we say, what do we say? We say K plus plus, right? So blah blah blah, then we hit the first one that's not the same, then we need to go one step back. Okay, actually no, we hit the first one that they're not the same, and we can go to because I need to know the distance, right? So the distance towards the end, so 1 2 3, which means from this to the end. So if it's 1 2 3, 3 minus 1, yeah, so it's the length minus this. Okay, so we shall say if this dot, no, p1 dot size minus K plus p2 dot size minus K is smaller or equal to distance. If that is, then what are we doing? We are counting the number of pairs. Then rest plus plus plus. All right, there's no rest, so we need to define an int rest is equal to 0. Right, so we go through this. Done. Back up, try it again, back up, try it again, back up, try it again. And then we'll just go through all of them. Right, go through all of them. And yeah. At the end, we'll just return. Let's see. What is the judgment? Yeah, we'll run all of them just to give it a shot. Take a look. Looking pretty good. So I think we're good to go. So we're gonna say this is LeetCode 1530, right? So we find the path from root to all the leaves and save them in a hash map. Okay. Then we go through all pairs of leaves, use their paths to find the lowest common ancestor, and then compute their minimum distance. And after that, the solution is self-explanatory. I will call it O(n) squared times log n. Okay. Well, technically we can say O(n) plus O(n) squared. DFS take O(n). This is taking O(n) squared. This K will go through log n. So that's kind of the analysis of the whole algorithm, and let's hope it's not wrong. We can throw in something interesting. For example, we can say 1 2 3 4. We can do 4, right? For example, we can do 1. For example, we can do this and call 3. Or for example, we can do this and call it, and I guess it's fine, 1, I guess. Run them and see what we get. Pretty promising. I'll run it, it will pass, we call it a day. But the timing is horrific. All right, definitely there is a better way. We cannot call it a day. Okay, so why is it so slow? That's a good question. Why is it so slow? It's slow because I'm only saving. Interesting, it's just slow. Yeah, we are looking through this, but maybe we can do it better. Yeah, because we are recomputing a lot of stuff that we don't have to recompute, right? And how do we know that some does not require recomputing? Maybe as we are getting them back, I don't know, can we? Yeah, maybe we can. Maybe we can. So what I'm saying is, as we get them back, right? So you're at 2, you catch 4 and 5, and then their distance is good, so you record 1, right? If 6, 7 is good, you record 1. And then you're going back to 1, and then you get a new set, right? You get a new set, and which means whatever happens here is already handled. Whatever happens here is already handled. So now what you need to do is this towards all this, this towards all this, right? Because that will be the first time that these two meet each other, right? That will be the first time these two meet each other. So when they meet each other, you check, right? You check, and if it's good, right? If it's not good, then we go up, we go up, we go up, we go up, all the way go to the top. So by doing this, we still do ON, and at each level we have to go through the leaves, right? The leaves. And I'll say at most we'll do it ON squared time, maybe. And then there's no mapping. There is still mapping though. There is still mapping. Yeah, but you go up every time you hit a node. You get all the left children, all the right children, and within them we don't need to consider, we're just between them, right? We consider between them. And we find the smallest on the left. We don't even need to record the nodes itself. We just need to know the distances, right? We just need to record the distances, because all we need is, we just need to return the distances, and then we we get the distance on the left, we get the distance on the right, and we can maybe sort them at every level. We can sort them, or we just go through everything, and then we say, and once there is not one that is available, right? We go from the smallest on the left, so we sort both. Okay, we sort both, or Java has sorted list, right? Let me see. I think Java has sorted list. Sorted list. Do we have sorted list? So there is a sorted set, but it's sorted. Sorted map. I think we need sorted map. Oh, yeah, sorted map, because I need to know the count. Right, so we have sorted map, basically a sorted counter. The keys is the key is not the value. The key is the distance, right? The key is the distance. What API do I have? Return the first key, the last key. That's all I need. First key and the last key. Right, the first key. So yeah, if I have some distance here, you know, I have some distance 1, 2, 3, and then they have, you know, some value, and some value. And here we have also 1, 2, 3, some value. So if the largest on the one side plus the largest on the other side, if that is still smaller equal to the distance, and then we can have all of them. Every single one can match with every single one here, right? Everyone can match with everyone here. That's just the distance. Yeah, we have like these nodes. We have distance, right? And then we have those nodes and those distance. And as long as it's all good, then everybody on the left can match with everybody on the right. So it's just a multiplication of the sum on this side and the sum on this side. We multiply them together. That's that. But sometimes it doesn't work. Then we'll just go through this, go through every single one until we fail. The second one, go through every single one, just be more generic. That, I think, we don't even need to be ordered. It's just gonna be a map. Yeah, we're just gonna do the map. Okay, so we're gonna have a solution number 2. So this is a 1, right? And we're gonna have solution number 2, which will look very different because we're trying to make it faster. This first one is so bad. So bad. Alright, so this is solution 2. So the goal is, yeah, this is another solution because solution 1 is too bad and too slow. So this solution will DFS the tree, and for each node it will acquire a counter of all the distances from the node to its leaves, right? Then we will iterate across the 2 counters from left and the right subtree, right? And identify the number of leaf pairs whose distance follows the sacrifice requirement. All right, but for this one, we still need private map of integer and integer. Right, this is what we can do: integer and integer. DFS tree node, and I don't think I need another thing. We do need int res equal to 0. Okay. All right. So again, if root of node equal to null, and then we're gonna return a new hash map. Otherwise, I just say map integer current equal to new current counter equal to new hash map. Okay, and then we're gonna do this, say counter, right? Now, if node is not equal to null, we're gonna say, oh, we need a nope, we need to go through its children first, right? We need to go to children first. So we're gonna say map integer LC left counter, so it'd be DFS node.left map integer right counter DFS node.right. Okay, so now we have these two, we have the left and right. We are going to do myself, right? Myself. Basically, what we're gonna say is the left counter, we're gonna make some modification to it. So everyone on the left counter need to be +1. Is we're focusing on me, right? It can be +1. So we're gonna say for int key of lc.keysets. We're gonna say lc.put k, lc.get k +1. Okay, for int k rc.keyset, same thing, rc.put k rc.get k +1. Okay. Next, we are going to say, because that's LC and RC, right? Basically, this one already prepares them, right? This one prepares them. This is the counter that prepares them. Now we're gonna go from right to left. Okay, let's also do this int distance. Okay, int distance. And the first thing we're gonna do here is this.distance equals distance. Okay, now we're gonna say for int k left key. That's actually better. That is actually better. I agree. Okay, so we're gonna say left key. All right, so that's gonna be left key. So we have the left key, and now we're getting the right key. We add them together. Yeah, we add them together. Okay. So the left key, and then we do the right key. Yeah, this is actually wrong. This is actually wrong. We're gonna delete this. This is actually wrong. What is right is we have the left key, right? And then because the left key is the distance. Okay, the key is the distance, and what we need to do is we're gonna get the right key. Okay, for int right key, right dot key set. Okay, so now we have that. We have the left key, have the right key. Then we're gonna say if left key +1 plus right key +1, if that is smaller or equal to this dot distance, right? If that is true, then we have pairs, right? We have pair. Then we say res plus equal to lc dot get left key, because that's how many nodes width has this distance on the left hand side, times how many on the right hand side, right key. Okay, so we do that, right? And after we're done with this, right? After we're done with this, we just go through them one by one. Okay, so all of them will be handled. All the keys on the left, all the keys on the right. Now we're gonna merge them into the counter, the current counter, right? So what we're gonna say is for int left key dot key set again. We're gonna say counter dot put left key counter dot get or default left key 0 plus lc.get left key. Okay, so this is actually not true because we increased its distance, so it should be plus 1. Right, that's the distance. And this is also plus 1. It's distance. Then this is the count, right? This is the count. So we do that, and we will do right. We'll do exactly the same for the right. So we're gonna have a right key of right. I'll put right key plus 1, and then this is gonna be right key, and this is gonna be right key. Okay, so that looks good. All right, we get the left key with the right key, and we're gonna do one more, which is itself. So counter.put 0, because our distance is 0, is 1. We have one node with distance 0. So we do that, and we'll return counter. Then what we're gonna do is we'll run dfs root, and then we'll return this .rs. All right, let's take a look. Oh, got a bit nervous. This is a very different solution compared to the other ones. Cannot invoke int value because return is null. Because this is RC. Two should be 1. Left key is distance, and I say distance, so either left, right, left all the way down. So basically this all do left, and then this all do left and nothing, so we come back here, so we have a left is an empty, right? It's empty. Then I do right, and this left and right both are empty, so basically nothing happens, and then counter put itself 0 1 and return this. So for this 2, what I have is right. What I have is left is nothing because the LC key set is empty. So basically it's nothing. So I can't do anything. And then for here, left key is nothing, but right key is something because I can say right key is a 0. So 0 plus 1, we have basically have 1. And 1 plus the right key is 1, so it's 1, so this one will have 1 1, right? Distance 1 will have 1 node. Okay, so we handled this, so that's and a 0 1 and a 1 1 return here. Okay, now we go here, shall be 0 1, so this one also has 1 1, so the left is 0 1 and a 1 1. Yeah, so on the left hand side, I think from the perspective of 1, this one returns 0 has 1, 1 has 1, 0 has 1, 1 has 1. On the right hand side, it's gonna be 0 as 1, right? So we go through this left hand key and a right hand key. Oh, because this is not a leaf. I see. Okay, so this is what we need to do. We need to identify if it's a leaf. How? Easy. We don't put this in. Easy. Easy. Hold on. We have a few. So I think we have LC here. This should be RC. But what we need to do, blah 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 blah. And this is all fine. This is fine. This is not fine. Okay. We'll only do this if no.left is equal to no, and no.right is equal to no. Only when this happens, then we will do this. Yeah, we can say leaf. Right? Otherwise, we don't do it. Otherwise, we do not do it. Okay, let's try this one. Or run it. That is correct, and I have high hopes for this one. Oh, I think this one is... I would say... I actually don't know what the runtime is, but we'll do it much faster. Much faster. We're talking about a 10 times. Okay, a 10 times improvement, but it'll be hard for me to analyze its big O notation. Well, DFS, we know every no goes once, okay, and so that's ON, and on top of ON we have to go through the distances. So what is the different types of distance? Well, because the distance at most is 10, so this is actually ON because it doesn't grow. Right? It just does not grow. I mean, that's a weak argument, but what I'm trying to say is this multiplier is very small. Okay, and the multiplier is very, we can just say OD times N, right? D times N. The D is the distance. Technically D squared, right? Technically D squared. Yeah, it's just D squared. So we can say this is a ON times D squared, right? Since D, where D is distance, so where D is distance, the total number, the different types, possibilities of distances. Now, since the problem has set D to be no more than 10, this solution is much faster than solution 1. Wow, this is actually a good interview question. I'm gonna mark it as a good interview question. I like it. I think it has a good potential. To me, all good interview questions need to have at least 2 solutions. A straightforward solution and a much smarter solution. All right, let's see. Graph conversion and BFS. What the hell is a graph conversion? Oh, it's convert a binary tree into an undirected graph. We can run BFS from each leaf node. And for each leaf node, the BFS encountered within a given distance, we count it as a good leaf node pair. Okay, this part I don't really understand. So we have traverse trees. We got the leaf nodes. So from all leaf nodes, for each leaf in the leaf node, get a queue. Oh, I see. From each leaf node will go out. Okay. From each leaf node will go out BFS within a given distance. And then we capture all the other leaf nodes. If it is in the leaf node, then we do it. And because we are adding them twice, so the answer divided by 2. Okay, I get this one. Post order traversal. I hope this is this one. Yep, I think this is this one. Okay, we have the similar structure, right? If it is smaller than this, yes. Yes. This is good. N times d squared. Exactly. Look, n times d squared. N times d squared. Great. Wow, I think this is a good. Yeah, it's good. All right, time to train. See you guys tomorrow. Adios.